Good morning, everyone.
Andrea.
Do you see my screen?
Yes, yes.
I'm Andrea Stefanoni, and today I'm going to present detecting security patches in Java projects using NLP technology. So the main problems comes from the fact that open source software is becoming more and more popular over the year because its ability to reduce costs in production and speed up the production of software. But in some of these code bases are present some vulnerabilities that are not detected yet. So it's probable that if we include other code in our code base, we are increasing the risk of vulnerability. So we want to detect the patches that may solve these vulnerabilities, analyzing the new changes that are made to the dependencies in the code base. So a patch is, as we can see in the right image, is the new changes that are made to the code. Highlighted in red, we can see the code that is deleted, and in green, the code that is added. So we consider the security patches as the patches that solve this vulnerability that are present in the code. This goal is to help to the software administrator to decide when to update the dependencies in their code, because it's a costly operation and requires many times. So we decided to analyze the code as a natural language, because the code is a type of language. There are some other studies that has done this, like CodeBERT and like CodeVec, that are specific NLP models trained on both code and natural language to create code and comments. So regarding specifically the patches, we can see that PatchRNN proposed a twin model with LSTM to analyze separately the added lines and the deleted lines, and merging them at the later stage to classify the patches. And this is done on C code because there are many, the most of the resources are available in C and C++ code. Another paper is CC2VEC that uses a hierarchical attention network, which exploit more the structure of the patch, because it's divided in lines, and lines is divided in ANK and then in files. So this allows to exploit more the structure, and this also uses the added and deleted lines separately. The only paper that I found using Java code is Commit2Vec, that is based on Code2Vec, which extrapolate the a triple of tokens from the code, and using a method similar to bag of word eliminates the context embedding and analyze the deleted lines and the added lines separately. Our approach is based on twin model, and we analyze the added and deleted lines separately with a transformer based architecture with Java code. So our research question is the difference in the updated code enough to classify these patches? And is also possible to classify the type of security that is solved or not? And is CodeBERT one of the best models to classify these patches? To do this, we use two datasets. The first one is a private one collected by the BRICT. It contains 1100 security patches and are with binary labels. And there are 123,000 rows that are not security patches. So to solve this highly imbalanced problem, we follow the example of all the other methods in the literature that undersample the majority class to have an easier problem to tackle. The other dataset is the one published by Ponta in the paper, a manually created dataset of fixes of vulnerability on open source software. It contains roughly the same number of security patches, but is as a multi-label classification with the CVE label. Since there were too many labels with respect to the available data, we clustered them in 5 macro categories, leveraging on the hierarchical structure of these labels. As for the preprocess, we extracted the added and deleted lines from the patch, and we substituted the common string and number with special tokens, and we divided the words based on the naming convention of the variable and functions, such as snake case and camel case. Then we removed all the stop words and special characters that are not used in Java, and lowercase everything to have a small number of tokens. For the evaluation, we used 20% of the data for testing and the remaining 80% for cross-validation, threefold cross-validation, and using the F1 score. So we started the methodology testing 3 different types of embeddings. The first one is a randomly initialized 32-dimensional vector. The second one is word-to-vec trained on the whole debricked dataset with 100 dimensions. And the third one is the pre-trained code-to-vec embeddings with 128 dimensions that is trained on their dataset of Java code. The best one found was the first one, mainly because I think it's more focused. It can learn more on the specific type of security issues or features. And then we tested the baseline models. We tried the XGBoost using some handcrafted feature taken from some old papers doing this task. And we tried an LSTM with the added and deleted lines concatenated with a special separator token. For the other models that we used the separate added and deleted lines, we created a combination layer which merges the embeddings, the feature extracted embeddings, using a concatenation, multiplication, subtraction of these embeddings and the cosine Euclidean distance. The first model is the PatchRNN, which uses 2 twin LSTMs that share the same weights of the parameters and the same structure. The second one is the hierarchical attention network, which focuses the attention on as a word encoder, a hunk encoder, and a file encoder. And then this last feature vector is the one for the added and the other one for the deleted line, always with a twin structure. And then we tried CodeBERT, that is the version of Roberta trained on code with multiple languages, one of which is Java. We tried with a fine-tuning, but it did not achieve a good result. So we froze all the layers of the weights, and we trained only the classification layer. We did this with the same structure of the first LSTM, with the input concatenated and with the input separated and the combination layer. The same goes for the transformer and the patch transformer, which is a few layers of the transformer architecture with the embedding similar to BERT, but with few parameters, and this was not pre-trained on any kind of task. So the first experiment was a binary classification on the first dataset, and we can see that the transformer has the best results. And with the Colbert didn't achieve the good results, mainly because the pre-training technique was not too relevant with the task, and the data available for the fine-tuning was not sufficient for fine-tuning all these of these weights for these parameters. Then we can see also that all the models that has the input separated, so in two different models, achieve a worse result with respect to the one that are concatenated. This may be because of the worse merge or of the different inputs that are present in the code. That like the differences between the old code and the new code. On the second experiments, we used the second datasets, and we tested the top 3 performing models. The results are not great. This one is the macro F1 score, and the dataset was slightly imbalanced, and the performance of the not very common classes are really awful. So the result is we cannot classify well the using a multi-label classification, this type of security patches. And but we see always the transformer as the best performances, and separating the input worsened harm the performance from the transformer and patch transformer. So concluding, we only use Java code for as data, and we could have tried using C and C++, since they have more resources published online, and always most of their resources focus on that. So as a future work, we can try to use both of the language and try if a multi-language model can improve the performance on the Java-based code. And we only use natural language processing as techniques, but also other research has been done on graph-based representation like abstract syntax tree. But this needs to have all the new code and old code to extract this graph representation of the code, and this is another challenge that needs to be addressed. Another future work it can be to use CommitBert that was released. The paper was released in this year, but the code and the model is not publicly available yet. So once this model becomes available, will it be possible to apply this model on this task? And maybe it will have a better performance with respect to CodeBert and the transformer. Concluding that the transformer was the best model among the one tested, and we managed to classify the security patches in a binary way with a good accuracy. So we didn't use any pre-training because the model, the pre-training models didn't perform as good as the non-pre-training one with less parameters. So that's all. Thank you for the attention.
A very comprehensive presentation. Would anybody have any questions? I see that there are no more questions. If it's ready, if anybody has any comments, we still have some time, 5 minutes. I can make some comments. I am not entirely familiar with the project on detecting security patches, but I wonder if there would be any other types of transformer models that can be used for transfer learning in your application.
Okay, I think that any model that creates an embedding at the end can be used. In this paper, we tried with CodeBERT because it was the one that has the pre-training more similar to the task that we wanted to use, since it was creating learning from the code and text to create an embedding at the end. But I think that any model like that creates an embedding, like I don't think that the GPT or T5 can work like right off the shelf, but with I think that with some modification or using like they making a question to the model and watching the generative answer can also be something to study.